Hi, hello. I'm Baron. This is like the 7th time I've had to write this script. There are many reasons for this. Mainly it's because instead of this video being like, ooh, check out this cool thing I did, this video is more about a different type of coding structure, which is kind of hard to explain. Another reason is because I've been running my brain away with an absolute ton of anime recently. And though I would never tell the general public how much of a weeb I am totally okay with saying that machine learning is a different subject altogether from the things I've done so far. Yes, it's coding, but the concepts and ideas behind why you are coding things the way you are is far different than the press F5 and see if it works type of programming that I've done up till now. I know this video is titled Genetic Algorithms Can Eat My Ass or something like that, but genetic algorithms are the first step to understanding machine learning. At least that's what I've read. I don't know, I'm still learning. So, in classic Bear the Coder fashion, instead of creating thoughtful and insightful content, today we're going to figure out how to make robots do the horizontal monster mash. Let's talk about it. Why does every girl in anime have to have absolutely huge boobs? I mean, massive Tahangara cougars. It's ridiculous. Almost as ridiculous as every programmer on YouTube talking to its viewers like they all have 4-year computer science degrees and worked for Google at some point. Why can't we just converse like normal people? So anyways, genetic algorithms use Darwinian theories to algorithmically produce viable results using unconvoluted data structures mimicking the chromosomes typically found in living creatures in the real world. Or, in layman's terms, genetic algorithms mimic evolution and natural selection in order to create an optimal result for whatever problem you're trying to solve. Basically, if you take the giraffe for example, it didn't always used to be the long-necked freak it is today. But, turns out, having a longer neck helped it survive better in a multitude of ways, outcompeting giraffes with shorter necks. Because it survived better, it had a better chance of creating offspring, which, in turn, inherited the same long neck. After millions of years, those born with longer and longer necks survived better and better. Like a positive feedback loop, now they all walk around above the treetops like the freaks of nature that they are. Genetic algorithms are kind of like that, but instead of using giraffes, we use a population of bots. To explain this, we are going to use the knapsack problem. For those uninitiated, the knapsack problem is this. You have a certain number of items, each with varying weight to them, and you also have a backpack that can hold a certain amount of weight.
The goal is to fill the backpack using these items.
The best solution is to get as close to the bag's weight limit without exceeding it. If it goes over the weight limit, the bag breaks. If this is your first time hearing about the knapsack problem, don't worry, I'll say it for you. This problem is pointless. Everyone knows it's okay. The only purpose of the knapsack problem is to explain genetic algorithms because of how complicated the answer can be. Don't believe me? Okay. If I were to present you with a list of 10 items, it might take some time, but you could probably find the best out of the 10 to fill the backpack, right? What about 100 items? Not as easy, but I bet you could still do it. Well, that's not exactly the same with a computer. Basically, without some programmatic intervention, the computer's best option is to brute force it by trying every possible solution, then selecting the best one. Well, those well-versed in brute force methods know exactly what I'm about to say, but let's say you have 100 items, then you have 2 choices per item. Either include or exclude that particular item. This means with 2 choices and 100 items, you have 2 to the 100 different possibilities the computer has to try. That's 1.2 nonillion possibilities. That's a 12 followed by a fuckload of zeros. 29 to be exact. And if we consider that a computer can do 2 billion calculations per second, means it would take a computer 12 trillion years to try all possibilities. That's almost as long as Betty White has lived. So the obvious answer is to not rely on a computer and just do it yourself, right? But what if you also had 10,000 backpacks you need to pack with 10,000 sets of completely different items? And this is the primary reason machine learning and genetic algorithms are as popular as they are. Because where human capabilities break down, we need machines to take up the task. Which is why you can more easily identify whether something is a cat or dog based on more complex logic and understanding than any computer can hope to achieve at this point in time. But if we asked you to identify and sort through a billion photos of cats and dogs, you'd probably wonder at what point did you venture into hell? So how do we solve the knapsack problem using a genetic algorithm, I hear you asking? Which is weird. How did you get in here? Get out of my house. Genetic algorithms only use 3 key phases: selection, crossover, and mutation. Selection is choosing the bots to breed. Crossover is combining two parents' DNA, or typically what normal humans call doing the nasty. And mutation is an arbitrary or random change in the DNA. To go through these steps, we need to create our first population of bots. These are usually represented by a separate class or object that can hold information. And these bots will be the ones doing the work and selecting the items to put in the backpack. But the first population is dumb and has no context or intelligence, so instead we give the first generation a list of all the items, and for each item we randomly tell it to either include or exclude that particular item. This list is called the chromosome. Every entry in this list is called a gene, which is a great way to think about it, but instead I like to think of it more as a question and answer type of decision tree that is usually represented as a list or array. For example, if we have 100 items we need to pack, we have 100 questions we have to ask. Should I include item 1? Should I include item 2? Etc. all the way to item 100. You have two possible answers, yes or no. Basically, this means that every index of the array represents a question, and the value of the index is the answer to that question. So, in our situation, our chromosome needs to be a list or array of length 100, and considering the answer is either yes or no, we can use Boolean values as the type. Now that each bot in the population has its list, we can start the selection phase. To start the selection phase, we first have to test how each bot did. Considering each bot has a list of items they want to include in the backpack, we check each bot's list, tally the item's weight, and test to see how close to the weight limit they got. If they are under the weight limit, they get a score based on how close they got to the weight limit. If they are over the weight limit, they get a big fat 0 for the score. This score is called the fitness value. And as a spoiler for my next video, this is definitely not the best way to do this, but it still works. With each bot now having a fitness value, we can select which bots to breed. This can be done in many different ways, but the three most popular is through either roulette wheel selection, tournament selection, or truncation selection. Roulette wheel selection is exactly what it sounds like, but the numbers on the roulette wheel represents each bot, and the space each number takes up is proportionate to the bot's fitness value, meaning the better the bot performed, the better chances it has of being selected. And I absolutely hate the name roulette wheel selection, as it's not conducive at all to what is actually happening programmatically. As far as I know, most languages don't have a roulette wheel function, so instead I like to think of this as more like a raffle system. Each bot is given a certain number of tickets based on how well they performed, and one by one, tickets are drawn from the raffle box, but instead of discarding a ticket after it's drawn, you put it back in the box. And I feel like it's easier to understand when you think about it this way. Tournament selection is basically selecting a small group of random bots, have them compete tournament style, and selecting the winner, repeating this process until you have enough bots selected. Or, as a better way to explain it, select 10 random bots out of your population of 100, then out of that 10, select the best performing one. Truncation selection is the simplest and easiest to understand of the three, and means that you sort your bots based on performance and select the top X%, most commonly the top 50%. It doesn't matter which selection method you use, they each have their benefits and downsides. For the knapsack problem, we are using truncation selection. With the bots selected, we can proceed to the crossover and mutation phase because they happen at the same time. As I said, crossover is basically letting your bots make premarital under the watchful eye of the Lord, and a mutation is just some random change in the chromosome, both normal in the real world. But the real world is imperfect, and it sucks, so the first step of crossover is cloning. I know, the whole Darwinism effect we are going for kind of gets thrown out the window, but mutations are not always good. Take humans, for example. We used to be hairy and have hands for feet. Now we have to wear clothes and sunscreen and go to work. Hardly the optimal version of ourselves. To prevent evolving backwards, we use cloning. We take the top 5 to 10% of the previous generation and clone them into the next generation. By doing this, we ensure the algorithm always has to compete to be better than the last generation, kind of giving it directional context, always pushing it forward. The remaining population is created the old-fashioned route. Basically, when a mommy bot and a daddy bot love each other very much, the information each bot carries is combined by a method called splicing. Splicing is like picking a random number, then telling the parent bots to rip their list at that random number and then swap the bottom half of that list with their partner, making 2 new lists they can pass on to their children. Why does this work? Well, it's basically still random chance, trial and error, that kind of thing. But by splicing chromosomes together, instead of deriving from complete randomness, we are randomly selecting our lists based off of lists that have already worked before. Thus, instead of our chromosomes being all over the place, we're hovering around the area we need to be at. But this doesn't always mean we will have the best solution. This is where mutations come in. Mutations serve one purpose and one purpose only: more variety. As I said before, 100 items means 1.2 nonillion possibilities. If we have a population of 100 in each generation, we are only ever deriving our solutions based off the first 100 possibilities. And if none of these possibilities are good, the likelihood of future possibilities being good as well is slim to none. To fix this, we need subtle arbitrary changes in each generation to increase the variety, making it easier to find better solutions. And this is as easy as just picking a random number between, let's say, 0 and 100, have the bot guess a number. If it guesses right, you change a random value in their chromosome. How often you do this is called the mutation rate, and getting the mutation rate wrong is the best way to prevent your algorithm from producing the best results. Too many mutations per generation provides too much variety, and the algorithm is basically no better than complete randomness.
We are so random.
Too few mutations, and there is never enough variety to evolve into better solutions. So what's the optimal mutation rate? There's no way to know for sure. It really depends on the problem you're trying to solve. The best way is to just test different rates and see if you get better results. As a rule of thumb though, for my testing, a mutation rate of 1 mutation per bot seemed to work best, so you can start there. With mutation done and the new generation created, you just loop that generation back to the selection phase and start over. The higher the population count per generation and the more generations you let the algorithm run, the better the results. So create as many bots as your computer can handle and let the algorithm run for as long as you can manage. Eventually, after a few thousand generations, the algorithm will eventually get it right with fairly high accuracy. And instead of it taking 12 trillion years, it really only takes a few minutes. And that's it. It's been a while since I wrote a script this long, and this is only a third of what I wanted to talk about. In part 2 of this series, I'll be doing a code walkthrough of how I solved the Knapsack problem to give you a better idea of how genetic algorithms work practically. And in part 3, we'll bring genetic algorithms into Unity and have it play Flappy Bird or something. Like, comment, and subscribe down below. If you do, I promise I'll buy you something for Christmas. Okay, bye.